Hello and welcome. We are going to be talking about mesh analysis today. Mesh analysis is one of the circuit solving techniques that goes hand in hand with nodal analysis. So to review, we have looked at nodal analysis before, and the primary consideration for nodal analysis was the fundamental equation, Kirchhoff's current law. With nodal analysis, we first identify all of the nodes, then we assign voltages to each of those nodes, then we write the equations, algebraically simplify, and then solve for the voltages. However, realize that in nodal analysis, even though we have voltages as variables, the equations that we write, each term represents a current. Now, mesh is the companion. Mesh analysis assigns a current to each mesh, and then we apply Kirchhoff's voltage law. Now remember, with Kirchhoff's voltage law, if we sum up the voltages across a loop, once we get back to our same point, then those voltages will equal zero. So first of all, let's take a look at what we mean by a mesh. So a mesh is a loop which does not contain any other loops within it. So it's one of the simplest loops that we can have. A loop is defined as any path that you get back to the same point after you traverse the loop. So that's a general term. But what we mean by mesh is that a mesh is a loop which is the simplest type of loop. So if we take a look at the left-hand side with the left-hand diagram at the bottom, we see that the loop goes and it encompasses two smaller loops. So we would not call that a mesh, that would be a loop, and the loop is not as simple as it can be. If we take a look at the middle one, that's definitely a mesh. So a mesh is a loop, but it's the simplest type of loop. And then we look over on the right, in the lower right, and we see that we have somewhat of a figure eight. Now that is a loop there, but it turns out that that's just two meshes sitting next to each other. So those are two meshes, even though they're connected. And if you take a look at the overall diagram, there we would say that we have four different total meshes, although there's many loops that you could make. So let's look at a more complicated circuit. Here we have the red path going around, and that does indeed form a loop, but that is not a mesh. If we look at another loop, we can see here the loop is even bigger. Now Kirchhoff's voltage law will apply when we apply it to that loop. However, we want to have as simple loops as possible, so that ends up not being a mesh. Where can we find the meshes? Let's see another one. We look down here at the bottom. That is the simplest loop that we could form with the lower portion of the circuit, so that ends up being indeed a mesh. Let's take a look at another one, the upper loop, and that's the simplest loop that we can have, and that ends up being a mesh. Okay, so these are the ideas of a mesh. A mesh is the simplest loop that we can have. And just as we had to first identify all the nodes for nodal analysis, the first step is identifying each of the meshes for mesh analysis. So for each mesh, what we're going to do is we're going to apply Kirchhoff's voltage law. Kirchhoff's voltage law comes in three different forms. We can say the sum of the rises equals the sum of the drops. We can say the sum of the drops equals zero, or we can say that the sum of the rises equals zero. Each of those forms is equally valid. However, for the purposes of mesh analysis, we're going to form a convention. And you could use any of them, but we are choosing to use the form the sum of the voltage drops equals zero. So let's look at the predefined voltages in this simple circuit. And in this simple circuit, we've got V1, V2, V3, and V4. And if we think about starting in the lower left, we can see if we just look at the variables labeled V, here we have a drop. You can say that we start at the top of the hill and then we go down to the bottom of the hill. So there is a drop V1. I know it's a rise of 7, but when we write it as a variable, we write V1 with this orientation, and that's a drop. V2, that's a drop. Keep moving. V3, that's a drop. V4, that's a drop. So if we sum up all of these, and we have an expression for each of these voltages, then that's going to end up equaling 0. Okay, so to do that then, we need to find a term for each of these. For mesh analysis, just like in nodal, when we have our algebraic equation, each element is going to show up as a term. Each element is going to show up as a term. This is pretty nice because we already have two of these voltages pretty much solved for us. But when we write the equations then, we're going to need the voltages across the 10 ohm resistor and the voltages across the 5 ohm resistor. And what we'll do is we'll use Ohm's law in order to determine that. So for the first voltage, V1, let's take a look at that. And we can see that the labeled 7 volts is an orientation as to a rise. So if we would write the expression for V1, V1 is going to be -7. Why? Because we are making it in terms of a voltage drop. Well, it's V2. We pull out Ohm's law, and it's going to be 10 times the current flowing in the loop. But we haven't defined the current. So we're going to define, and we're going to say that we are going to have a current I1. Now that current I1 is the same current that flows through each of these elements in this simple example. So now that we have our current, we can say that V2 is 10 times I1. V3 is going to be plus 3 volts because it's in the same orientation as the voltage source. And for V4, it's just going to be 5 times I1. Now, a note on this, when we said V2 has the plus going down and the minus going up, you can see that as this I1 winds around in clockwise fashion, in that case, the current I1 is entering the positive node of V2, and therefore V2 is going to be plus 10 times I1. Moving on to the next, then, what we want to do is substitute in those values for each of the terms, V1, V2, V3, V4, into the equation. And when we do that, then, remember this is what we had from the previous slide, then we have -7 plus 10i plus 3 plus 5i1 equals 0. And you can see that each of these is a voltage term that we're adding together, even though our variable is in terms of I1. Once we solve for I1, we have one equation, one unknown, then we pretty much know everything that we need to do for the circuit. If we were asked for what V2 is, and we had solved for I1, we plug it back into the equation for V2, and then we would get 10 times our solved I1 would be equal to the voltage V2. And this is what it is. Now, this is a very simple example, and when we have more than one mesh, we're going to have shared current. So let's take a look at this example here. We've defined I1 and I2 by those arrows there. And so that's usually the first thing that we do is we define I1 and I2. And we're saying that this is the current I1 that's flowing around this mesh and the current I2 that's flowing around this mesh. However, we have to be very careful because I1 and I2 are both sharing this 3 ohm resistor. So if we take a look at what is the current going down here, we can apply the KVL, and then we ask ourselves, what is the current flowing through the 3 ohm resistor as a function of I1 and I2? Now I1 is the current that's flowing through the 6 ohm resistor from left to right, and I2 is the current that's flowing through the 4 ohm resistor from left to right. And incidentally, I2 also flows through the 10 volt source, and I1 flows up through the 42 volt source. But what is the current in that 3 ohm resistor? Well, the sum of the currents in have to equal 0. So if we have the current flowing out, that's going to be equal to I1 minus I2. And we're going to need that in order to write our equations. So as we write our voltage equations, we'll have to realize that any shared element between two meshes is going to involve the difference of the currents of those two meshes. We'll now move on to our problem solving, where this will be our first problem that we'll work through together.